Organic Chemistry 2. So we finished up Chapter 17's content last class on Monday, and where I wanted to pick up at is question 17.13, which simply asks for each of these compounds here, determine which, if any, of the lone pairs are participating in aromaticity. So the bottom line is this. Let's say you have this compound that we're starting out with. We have a 5-membered ring. We have an oxygen. Obviously, you can see that this is a pi bond, right? This is a pi bond. And we have 2 lone pairs of electrons here. So here's the answer. The lone pairs are going to go into an unhybridized p orbital, right? Remember how I would draw this, right? I draw an unhybridized p orbital. Right? We know that there's some on all these carbons because, again, they have pi bonds. So that's no mystery to us. But one of the lone pairs will jump into a p orbital, right, which is shaped like a propeller or a peanut or whatever you want to think of. It will do it only if the compound can become aromatic by doing that, okay? So the bottom line is a lone pair will do whatever it's got to do to render a compound aromatic. So the question is then, if I put one of these lone pairs, let's say this one right here, if I put this in an unhybridized p orbital, how many pi electrons would I have? Okay, then I'd have 1, 2, 3, 4, 5, 6. Well, 6 is a Huckel number, right? Because when I have 4n plus 2 and n is equal to 1, I have a total of 6 pi electrons. So if I put this pair of electrons, okay, if I put this in an unhybridized p orbital and I render this oxygen sp2 hybridized, that means that one of the lone pairs is participating in aromaticity. And so the answer here, I mean, you could answer it any way you want, but you could just say yes. So there is a lone pair on that oxygen that is participating in aromaticity. If we move on to the next compound, so it's pretty similar to the first one, except we're replacing the oxygen with a sulfur. It's the same rationale, right? We already have the 4 pi electrons for sure in these pi bonds, right? So they are pi electrons. But then the question is, will one of the lone pairs here, either this one or this one, it's neither here nor there, but will one of the lone pairs of electrons go into an unhybridized p orbital, right? Let me explain it again, like a different way maybe. If I have that continuously overlapping system of unhybridized p orbitals, right, you see how they're completely overlapping like this. And if that lone pair, okay, if this lone pair jumps into an unhybridized p orbital, then I have a total of 1, 2, 3, 4, 5, 6. So I would have a Huckel number, right? I would have 6 pi electrons, right? It's 4n plus 2 when n is equal to 1. So if I just erase all this spinach here, okay, the same rationale applies. If this sulfur becomes sp2 hybridized, then yes, one of the lone pairs will participate in aromaticity. Okay, before I get your help with the next one, with C, okay, something else that you want to keep in mind with these type of questions is a lone pair, and again, there's only one lone pair here that we can even identify, the one on the nitrogen. The bottom line is it will go into an unhybridized p orbital. It will participate in resonance if it can render the compound aromatic, but to avoid being anti-aromatic, okay, the lone pair will also do whatever it can to do that. Okay, so whenever we have something that might be anti-aromatic, a molecule will always seek whatever it can do to avoid becoming anti-aromatic. So with that in mind, my question is to you: would this lone pair, where's my blue pen? Would this lone pair participate in aromaticity? Yay or nay? Yeah, absolutely not. Right? Because if it did, right, let's just say if it did, and it doesn't, okay, we've established that already, but if it did, you'd have a continuously overlapping system of p orbitals. Okay, I'm drawing a p orbital on all the sp2 hybridized carbon, but if we made this nitrogen sp2, which it's not, but I'm just explaining this because I'm your instructor, then you'd have a total of what? You'd have 1, 2, 3, 4, 5, 6, 7, 8. That's not a Huckel number, is it? That's 4n number of electrons when n is equal to 2, right? Then you'd have 8 pi electrons, which would render it anti-aromatic. Okay, so this molecule doesn't want to be anti-aromatic. So what's the answer? Could anybody tell me what this molecule does or what this lone pair does in order for this molecule to be non-aromatic as opposed to anti-aromatic? How does it avoid that? Can anybody give me a quick answer? You know, just a very short answer. And if you have to give me a long answer, that's fine too. But there's something the lone pair can do. It can become sp3 hybridized, right? If that nitrogen is sp3 hybridized, okay, then the lone pair is in an sp3 hybrid orbital, okay? So we don't have a continuously overlapping system of p orbitals, and the compound is non-aromatic. So let's erase all this. So now, if that's nitrogen, again, if it's sp3 hybridized, the compound is non-aromatic, okay? And the answer is no. The lone pair will not be participating in aromaticity. All right, let's take a look at the next one. This one is called thiazole. This one here, common ring in some drugs or some types of drugs. Anyhow, it's neither here nor there. But you see, we've got a lone pair on the sulfur, and we've got a lone pair on a nitrogen. Well, you might remember that earlier on we said if an atom contains or possesses both a lone pair and a double bond, both of them can't participate in resonance. That's impossible. Okay, so only one of them is going to participate in resonance, and it's going to be the pi bond, isn't it, right? So we know that that nitrogen is going to be sp2 hybridized because it's got the pi bond on it. And that means that this lone pair is not going to participate in aromaticity, right? It's not involved. However, the lone pair that I have on the sulfur, the one that I have circled in green, I'll just ask you the question point blank. Will that pair of electrons participate in aromaticity? Would it do that? Would it have a reason to do that? Absolutely it would, right? Why? Because if the hybridization of this sulfur, where's my green pen? If it's sp2, right, that means that one of the lone pairs is in a p orbital. This nitrogen already has a pi bond, so it already has a p orbital, as does the carbon, this carbon, this carbon, right? So if there's a p orbital here, then I have a continuously overlapping system of p orbitals, and I've got a total of 1, 2, 3, 4, 5, 6 pi electrons that are participating in aromaticity. And so the answer here is yes, right? The lone pair on the sulfur, one of the lone pairs, is going to be in an unhybridized p orbital. The sp2 refers to the hybridization of the sulfur. And so this is going to be an aromatic compound, right? And the answer is yes, right? Again, we can keep going over the same things. 4n plus 2, where n is equal to 1. Therefore, we have 6 pi electrons. All right. What about the last one? I'll just throw it out there to my students. There's only one lone pair to be concerned about, and it's on the oxygen. Would that lone pair be involved in aromaticity? Is that lone pair participating in aromaticity? Right, again, the answer is no. Right, how do I know that? Because there's already 3 pi bonds in the ring. Right, I already have 1, 2, 3, 4, 5, 6 pi bonds. So I already have an unhybridized p orbital, right, on the oxygen. That's part of this pi bond right here. So why, in pray tell, would this lone pair get involved in aromaticity? It doesn't need to be. I already have 1, 2, 3, 4, 5, 6 pi electrons, which is a Huckel number, 4n plus 2, when n is equal to 1. And so the answer is no, right? This lone pair is going to be in an sp2 hybrid orbital. All right, so there we go. So we'll put here, the oxygen is sp2, and so the answer is no, because the lone pair is going to be in an sp2 hybrid orbital. And there we go. All right, give me a thumbs up if you follow me on that, or if you have a question, of course, stop me. In order to understand the concepts that we're covering right now, it does take thorough studying. Okay, it will take some serious thought. I've taught aromaticity enough to know that it's not one of those things like if I just tell you, okay, you throw chromic acid in a primary alcohol and it oxidizes. Okay, that's easy to remember, and I say you don't have to memorize the mechanism. Okay, no problem. But when it comes to the concept of aromaticity, it takes a lot of thought. Okay. So you're going to have to sit down with the problems and try them and try to understand why it is. I mean, I'm providing the best possible explanation I can based off of our textbook and what we've covered in class. But of course, if I've left any stone unturned or something in your mind, feel free to stop me at any point. So there we go. And we're going to look at a couple more practice problems that involve aromaticity. But I want to skip ahead down to the last problem that we didn't look at, and it deals with synthesis, right? Propose an efficient synthesis for each of the following transformations. All right, propose an efficient synthesis, so not something that's not 25 steps, something that's simple in terms of a synthesis here. So we're starting it with toluene, right? In C, we're starting it with toluene, which is methyl benzene, just a benzene with a plain old methyl group. And then we're making this compound here where we have a nitrile added, right? So we're adding a carbon, right? Here we have 7 carbons total. Now we have 8 carbons, right? There's a carbon here, so that's a new carbon. So we're adding a nitrile. But how are we going to add that? Okay. Could anybody make a suggestion based off of what we talked about last class of where I would start with the toluene molecule? And there aren't a lot of choices, are there? Could anybody make a suggestion as to where you would start? If you were just given toluene based on your knowledge of organic chemistry and what you learned in Organic Chemistry 1, what you've learned in this chapter and all of Organic Chemistry 2, right? The only choice that you would have is bromination and light. This is what we looked at last class. If I feel like we never covered that, let me back up here and let me show you. In section 17.6, we covered reactions at the benzylic position, right? We covered radical bromination, right? How do we do that? We use NBS, okay? So we're not going to use bromine and light to do that, okay? So let me go back here. We're going to use NBS and heat to do that is the best way to do a bromination at a benzylic position. So NBS and heat is going to be our first step. So let's go back here, back to the question. And if we treat this with, let me see here, what's the easiest way to do this? If I start it with my toluene molecule, okay, and I'll move it over here just to have a little extra space. If I treat this with N-bromosuccinimide, that's NBS, and I heat that up, I'm going to end up with this compound that we call benzyl bromide. Right, now I've got a primary alkyl halide. What can I do with a primary alkyl halide? Well, let's go back in our notes, okay? That slide that we were looking at just a few seconds ago. Right, if I have a primary alkyl halide, like benzyl bromide, shown right here, I can do an SN1 or an SN2. Well, what would the nucleophile be if I wanted to replace the bromine with a nitrile, with a CN? Could anybody tell me what the nucleophile would be? I just want to replace the bromine with that carbon and nitrogen. I want to go from here to here to put in that nitrile, right? Remember that when you have a C triple bond N, right, that's called a nitrile. Exactly. The way that we make a nitrile is from cyanide, right? Cyanide is a polyatomic ion from General Chemistry 1. It's also showed up in General Chemistry 2. If we treat this with sodium cyanide, what's going to happen, right? You should be able to draw the Lewis structure of cyanide, which is this. It's a good nucleophile. It's a weak base, okay? And it's going to do an SN2 reaction like that. And you're going to end up with the product, which is this. So we'll put our methylene here, and then we'll just put CN like that. So just a plain old SN2 reaction with our nucleophile, which is cyanide. I'm going to delete the mechanism just to save a little room here. But give me a thumbs up if you follow me on that one. So that is C. It's a 2-step process. So first was benzylic bromination using NBS and heat, followed by an SN2 with sodium cyanide, and that goes all the way back to Chapter 7 in Organic Chemistry 1. It's a good nucleophile, weak base, primary alkyl halide, bada boom, bada bing. All right, I could even ask you, based off of what you learned in Organic Chemistry 1, what would make a good solvent for this reaction, an SN2 reaction? We want a polar aprotic solvent, something like acetone or dimethyl sulfoxide, DMSO maybe. Anyhow, there we go. Well, let's try the next one. The next one is D. We have this This would be called cyclohexylbenzene, okay, or phenylcyclohexane. Either one would work. It's just like when you look up the name of a compound on Wikipedia. I don't know if anybody's ever done that before, but sometimes they'll have, half a dozen different names for the same compound. Well, here we have our aromatic ring, right? And we also have one proton at the benzylic position. So the same thing is going to apply here. If we take this compound, so I'm going to write it out like this, phenyl, okay, with my cyclohexyl group over here. I've got that one benzylic proton, but if I treat that with N-bromosuccinimide and I heat that up, what am I going to get? I'm going to get a substitution where I'm going to have a bromine in that place now. So now I've got a bromine here. Now I've got a tertiary alkyl halide. All right, I've got a tertiary alkyl halide. Well, what do we know about tertiary alkyl halides? They don't undergo SN2 reactions, do they? They undergo SN1s. If you don't believe me, okay, if we go back to the slide, they had the summary of all the reactions that we had taken a look at. All right, here's a tertiary alkyl halide. Okay, now how would I, put something with an oxygen here? It's through a solvolysis reaction, right, which is just an SN1 reaction, right? The leaving group leaves, the nucleophile comes in, we have a proton transfer. Now, if I wanted to do this particular SN1 reaction, could anybody tell me how I would do this to go from here to here? It's an SN1 reaction. Could anybody tell me what the reagent would be? It's just one reagent. Exactly. You'd put in water, wouldn't you? Right? You'd put in water because the first step in the SN1 is the loss of leaving group. You would produce this carbocation, right? Then water would come in as a nucleophile, right? Then you get a proton transfer at the end. Okay. Well, with all that in mind, if we go back to our question, now I want to put an oxygen in this place, okay? But I want to have a methyl group on one end. So instead of water, H2O, right? Instead of H2O, I'm going to use HO with a CH3, right? That's methanol. So I'll use methanol as my solvent in this case. So let's draw that out. We would take this and we would simply treat it with methanol. And this is an SN1 reaction. And that's a solvolysis reaction is what we call it. And you would end up with the desired product, just like that. Okay, there you go. All right, so that is D. And then we got one more. And I think we have enough room to solve it on this page. In E, I have a question for you. Is there a change in the carbon skeleton in E? Is there a change in the carbon skeleton in E? Yeah, absolutely there is, right? We have 6, 7, 8 carbons here. And then we have 6, 7, 8, 9 carbons. Oops. I was like, that's not right. We have 9 carbons here, and then we have 8 carbons here. So we're losing a carbon, and we're making a ketone. Now, what kind of reaction did we see where you lost a carbon and made a ketone? Could anybody tell me what the name of that reaction is? Where you lose a carbon to make a ketone. And I want the name of the reaction. All right, in terms of retrosynthesis, what I'm thinking about is this. If I was able to make this compound, so I'll just put it like this. If I had this alkene, there's a one-step process that I could go through to go from that alkene and to break this bond and convert it into a ketone. We have to go back to our organic chemistry 1, to the alkenes chapter. Could anybody name that reaction or maybe just provide the reagent? Yeah, so it's ozonolysis, right? Oxidative cleavage, right? So it's an ozonolysis reaction. Remember that? We would use ozone and DMS to do that, right? Well, if you understand that, then the question becomes, how do I go from here to here? I started with the exact same strategy I did for every other problem on this slide. Let me show you what I mean. So let's just delete all that. And the first step is going to be to take this compound, which is called cumene. My arrow's too long. There we go. So we're going to treat it with NBS. and we're going to heat it up like this, and you're going to end up with this compound like this. There we go. Like that. And you're going to have a tertiary alkyl bromide. Well, if I want to take this and convert it to the alkene that I was looking at just a few seconds ago, if I want to take this and convert it into this alkene, how would I do that? I would do that by an E2 reaction. Right, so I'm going to hit it with a strong base, right? Something that's a strong base, weak nucleophile. I mean, this is tertiary, so I don't really have to worry about substitution occurring there. So there's a whole host of bases you could use. You could use potassium T-butoxide if you wanted. You could choose that. We could use sodium methoxide. Doesn't matter. And yeah, let's just choose sodium methoxide. Students seem to like that, right? And again, you're an organic chemistry 2 student. You should be able to draw the mechanism that's occurring here, right? You have a positive charge here, a negative charge here. You have the elimination reaction, oops, like this. There you go, loss of leaving group and proton transfer simultaneously to make the alkene. And then in the last step, we're going to treat that with ozone and DMS, ozone and dimethyl sulfide. Sorry, it's a 2-step process. So ozone in the first step, and then DMS in the second step. All right, there we go. So those are some, just some syntheses that you would want to take a look at. If you go into section 17.7, we looked at, some other reactions. And I'm just trying to figure out where this question is. Did I take this from the back? Let me see here. Let me double check. No, it's from inside the chapter. So it's in reactions at the benzylic position. Yeah, 17.6. So it's in that section. And then right after that section, 17.18. Okay. So there's a few more questions in there. We didn't do A. We didn't do E and F. So I would recommend, of course, trying those ones. Okay. Those are all really good questions for you to take a look at. And there you go. Now, in terms of the spectroscopy of aromatic compounds, I mean, the reason I put skip it in here is because normally we don't go into a long lecture with our students in organic chemistry 2 about something that's taught in organic chemistry 1. But just as a reminder, you remember when you did IR on aromatic compounds? So aromatic compounds, right? We have sp2 hybridized carbon-hydrogen bonds, okay, like this. And they have an absorption just above 3,000. If you remember, we always took the ruler and then we draw a line at 3,000 reciprocal centimeters. And it's something we do in organic chemistry 1, but we can do it in this class too. Also, in terms of the overtones, students really seem to identify with the overtones for some reason. But the overtones, it says here 1,700 to 2,000. It's more like 1,667 to 2,000, but whatever, 1,700 is definitely close enough, okay? What else? We see aromatic stretching, right, between 1,650 and 1,450. It's usually 2 to 3 signals. When it's 3 signals, we usually have 1,450, 1,500, and 1,600. I've covered IR recently with Organic Chemistry 1, so I can attest to that most of the aromatic compounds you see, right, the carbon-carbon stretching, okay, usually is 3 signals, okay? Then as far as the fingerprint region, I don't really worry about those a whole lot with my students. I mean, if you want to take a look at those, you have in-plane bending around 1,000 to 1,300, and then to 700 to 900, you have out-of-plane bending. Anyhow, that's usually something that we only look at in the organic chemistry lab. So here's an infrared spectrum of ethyl benzene. So what's ethyl benzene? Ethyl benzene is this compound. You have an aromatic ring, right? And then you have an ethyl group on it. So if you take your ruler, here's my ruler, and you draw that line at 3,000 reciprocal centimeters right here, and then we usually draw another one around 1,500, okay? Just kind of my mode of attack with these kind of problems. You see that we have some signals right above 3,000, right? Those are the sp2 hybridized carbon-hydrogen stretching. Carbon-hydrogen stretching whereas these ones here are sp3, hybridized carbon-hydrogen stretching. Here are the overtones. Oops, I don't know why it does that. Here are the overtones right here, okay, which are again 1700 to 2000. Here are the aromatic carbon-carbon stretching. So this is all the aromatic carbon-carbon stretching. Okay. And then you have the bending of the carbon-hydrogen, which we don't, won't worry about a whole lot in Organic Chemistry 1 and Organic Chemistry 2 lecture. As far as the Nmr spectroscopy, you should remember that the aromatic protons have a chemical shift of around 7 parts per million. Right, so let's say you have the Nmr of Ethyl Benzene. Well, what are you going to see? You're going to see a triplet that integrates for 3 protons, right? Because those 3 protons are coupled to 2 protons. What do you see for the methylene group? You see a quartet, right? That is slightly more deshielded because of diamagnetic anisotropy, right? The magnetic field that's created by the pi electrons in the ring, so that has a deshielding effect on these 2 electrons here. And then you have the 5 protons, which are all in the aromatic region, which again is around 7, so 6.5 to 8 roughly. Okay, and then also some other interesting things. If you have a symmetrical para-substituted aromatic ring, you're just only going to see 1 singlet, right? Because there's going to be no splitting, right? Remember that protons that are identical, all 4 of these are identical. Protons that are identical or chemically equivalent, not chemically equivalent, but identical in identical environments, they don't split each other. But if you have a para-substituted ring where X and Y are different, of course, then you see a doublet of doublets, right? These 2 are identical, and these 2 are identical, but this one is coupled to this one, so you would see a doublet, and the same thing is true. This is coupled to this, so you see 2 doublets. So you get a doublet of doublets. And oftentimes, I don't know if you remember this from Organic Chemistry 1, but oftentimes that doublet of doublets will kind of slant inwards. It'll kind of be like this a little bit, where they kind of slant like this way and this way a little bit like that. Anyhow, so that's a para substitution on an aromatic ring. And then in terms of the carbon-13 of aromatic rings, you should be able to identify how many signals based on the substitution. So if you have something that's symmetrically substituted, that's para, you would only see 2 signals. If you have ortho substitution of the same group, then you'd only see 3, right? Because there's a plane of symmetry here. If you have para substitution and the 2 substituents are different, then you would see a total of 4 signals, right? Why? Because this carbon and this carbon are identical, this carbon and this carbon are identical. And then 6 signals, of course, if you have different substitutions in the ortho or meta positions. And there you have it, my friends. All right, so the number of signals in carbon-13 can really help you identify the type of substitution on an aromatic ring. And those signals, those carbon-13 signals for the aromatic ring, they come out around 100 to 150 parts per million.